Oh, quickly finish it. Quickly finish it.
Well, I only have like questions. I can most of it.
Okay, take a 7.0, right? Take out 7.0. Listen up, please. So we did A all together, right? Fairly straightforward. Sulfur is burning oxygen, so it's not a combustion reaction, even though it's got elements of a combustion reaction in it. But this is a formation reaction. Element and element makes a compound. Then aluminium oxide is heated and broken down into its elements. What we did is we did the skeleton equation, right? And I asked you to balance it, correct? Yeah, but then I didn't remind you to balance it at the end, so that's fine. Which one of these is the most complicated substance? So the first one, right? And I'm not going to do aluminium. Don't do aluminum first because it's the simplest one, right? So let's do oxygen. So we've got groups of 3 over here and groups of 2 over here. So we just need 3 and 2. And then that means we've got 4 aluminum, so 4 aluminums. No problem. It's all good. Then we went through Mr. Walton funds his retirement by reacting copper metal with silver nitrate. Did we actually finish this one all together?
Yeah.
I think we did, right?
No,
No, we
we didn't.
didn't.
It's the one in the phone.
So we react copper metal with silver nitrate. I think one of the hardest things for a lot of people is noticing that this is an ionic compound and getting the formula for the ionic compound. I still think that's one of the most difficult things for people. So what's going to kick out what? Copper is going to kick out the silver or the nitrate?
The silver.
The silver, right? It's definitely not going to be copper and silver together. You can't have 2 different positive ions together. You can, but it's not in the scope of Chem 20. So we're going to get copper nitrate. And why did I put the nitrate in brackets? Why are there 2 nitrates? Because what charge of copper is going to be more likely for us to get? 2 plus, right? So we need 2 nitrates. And then we got 2 silvers, and then we just balanced it. Blah, blah, blah. That's fine. Any questions so far?
Wait, so why is the copper 2 more likely than the copper 1?
Well, are you asking me why is it that in reality copper 2 is always more likely than copper 1? Or are you?
Why do we do that in this question? Like, why do we always?
So we're assuming that under like normal aqueous circumstances, we're going to make copper 2. We can make copper 1, but we can only make copper 1 under very like specific circumstances. We need to have very specific conditions in order to make copper 1. And we're just assuming, Aaliyah, that like regular temperatures and regular conditions will, for the most part, always make copper 2 plus.
How does that work with all the other covalent?
The first charge that's made is the one under very typical conditions.
Okay, so
the very first one that you're seeing, yeah. In your data booklet last year or 2 years ago, whenever you did Science 10, in your data booklet in Science 10, it used to be split up by top and bottom. I don't know if you remember that. Yeah, and it was always the top one that we would choose. It's the same thing here. It's just the first one that you see that under traditional circumstances, that's what we're going to get. Good. Okay. Then the next one. Aqueous chlorine is placed in the solution of sodium iodide. We did this one though, right?
Yeah.
Yeah. Good. Okay. The chlorine and sodium iodide makes sodium chloride and iodide. I forgot to put this is my last year's version of these notes. So sodium chloride is aqueous and iodine is going to be salt. No problem. Then I asked you to do propane. Propane is burned in a barbecue at the big year-end chemistry party. Okay. Propane. What is the formula for propane? C3H8. And what are we? Whenever we burn something, we react it with what? Oxygen. Perfect. So when we burn propane with oxygen, we're going to get carbon dioxide and water vapor. This is a big deal. There's a huge difference between liquid water and water vapor. And that's the balanced chemical reaction. Let me know if you need any help balancing. I'm not going to go through this a ton because remember we already went through how to balance hydrocarbons. Sorry, I got something stuck in my throat. Aqueous solutions of silver nitrate and sodium sulfate are combined. The first thing I want to ask you is what type of reaction is this? What classification? Double replacement reaction, absolutely. Okay, so we're going to get our silver nitrate and our sodium sulfate. And the silver is going to kick out the sodium, right? The cation and the cation kick each other out and they swap partners. I want to focus on states of matter here right now. So once you're done kind of either writing some stuff down or whatever, just pay attention up to the front. I'm not going to check the state of matter of silver nitrate, and I'm not going to check the state of matter of sodium sulfate because it tells me aqueous solutions of both of these things. If it's telling you that they are aqueous, just do as you're told. It's aqueous, no problem. AQ, AQ, perfect. Then we want to look at this, and so let's see. Sodium nitrate. It's not telling us that that's aqueous, but that's what we're predicting we'll get. Is sodium nitrate aqueous?
Yes.
Yes. How do you know? All nitrate compounds are aqueous. But yes, data booklet. So just as a little bit of a prelude to what we're going to do today, does sodium nitrate aqueous? When we have this thing in solution, does it exist as sodium nitrate? Or is it going to break up? Is this ionic?
No. Yes.
Yes.
Yes. Metal, non-metal, right? So this is ionic, and because it has high solubility, will the ions separate from each other?
Yes.
Yes. So I want to be very clear. We're writing it down as sodium nitrate, but it doesn't really exist as sodium nitrate together. It exists as sodium ions and nitrate ions, and they're independent of each other. They're floating around in solution, crashing around with other things, but they're acting independently of each other. Silver sulfate, is silver sulfate soluble?
Yes.
No.
No.
Solid.
How could we check?
Data.
Let's check the data. So I'm going to pull up my Chem 20 data booklet, and I'm going to look on page 5 of the data booklet. Nope, page 6. Here we go. And we're going to look up sulfate, and most of them are soluble, right? But do we see silver, down here?
Yes.
Yes.
Uh-oh, then it's not going to be soluble, right? So we're going to put a big old solid attached to it. And I'd put it beside it, but I don't have any room because I'm lazy and write too big. Any questions about that? Okay. Last question. I asked you, ammonium nitrate and potassium chlorate are combined as part of a big reaction. And so we've got ammonium nitrate and potassium chlorate. I'm just going to exit out of this if I can. We've got ammonium nitrate and potassium chlorate are reacting, and the ammonium, what charge does an ammonium ion possess? Positive. So it will kick out the other positive, right? So we get ammonium chlorate and potassium nitrate. Now, I said solutions of this, aqueous and aqueous. And then, so did anybody look at the states of matter? They should both be aqueous, right? Yeah. Good. No problem. Any questions about that? No? Alright. How comfortable are you with writing chemical reactions right now? How comfortable would you say you are?
7.
Yeah, okay, so we're getting there, right? It's okay if you're not 100% confident, but as long as we're starting to get there, then that's really good. That's a good indication that things are going well. Can't count and talk at the same time.
Oh no, you just broke your hand. I thought when you entered you. Oh.
Okay. Yeah, sorry, that's kind What I want us to do is you don't have to go back to the 7.0 notes or anything like that, but I just want us to look at the silver nitrate. I just want us to look at the silver nitrate equation with the sodium sulfate. Let's take a step back and let's think about each of these substances individually. So what happens here is you have a solution of silver nitrate. So the way I would kind of represent that is you've got a beaker. You've got a beaker with a solution in it, and if it contains silver nitrate, first of all, is this substance able to break up?
Yes.
It's ionic and it's high solubility, right? So instead of having silver nitrate altogether, what is this? What's actually in this solution?
Silver and nitrate.
So we've got silver ions and we've got nitrate ions. Okay? So that's in beaker number 1, right? If we're in a lab, we've got that in beaker number 1. Then I look at beaker number 2, and we've got a solution of sodium sulfate. Okay, what's my next question that I'm going to ask you?
Same thing.
Exact same thing. Is it able to split up? Yeah. So we've got sodium ions, and we've got sulfate ions. So please kind of keep this in the back of your mind. When you have a solution of silver nitrate, you don't really have a solution of silver nitrate. You have a solution of silver ions, and at the same time, you have a solution of nitrate ions. Is that okay? Yeah, okay. So silver and nitrate, when they're together in the same beaker, do they form a precipitate? When we check our data booklet, and I'm kind of going backwards here a little bit, but when I have nitrate combined with silver, do they form a precipitate? No, they don't. The combination of nitrate and silver, I don't see silver anywhere on here except for silver acetate. So the combination of nitrate and silver does not make a precipitate. And hopefully that makes sense. They're together in the beaker, and they're not doing anything with each other. They're just independently floating around, bumping off of each other, and they don't even really care that they're there, right? Sodium and sulfate. Sulfate, when it's in a beaker with sodium, do they make a precipitate together? No, they don't. Okay? When I add these two together, what types of ions will be present in this new solution? When I add these two together into a new beaker, am I going to get silver ions?
Yes.
Yep, silver ions. What other ions am I going to get? Nitrate ions. What other ions am I going to get? Sodium ions. What other ions am I going to get? Sulfate ions. Can any combination, when silver bumps up against the sodium ion, are these two things going to form a precipitate? Do you think a positive and a positive would like to form a precipitate? No. The nitrate and the sulfate, when they bump into each other, are they going to form a precipitate? No. Okay, we've already established silver and nitrate don't. Sodium and sulfate don't. What's the only other combination here?
Switch partners.
Switch partners. Do sodium and nitrate, when they bump into each other, are they going to form a precipitate? Sodium and nitrate? The only reason why I'm double checking is because you're hesitant. Look at the table. Do sodium and nitrate make a precipitate? I see nitrate here. Do you see sodium nitrate down here? No, so they don't make a precipitate. Okay, all right. So when they bump into each other, when the sodium ions and the nitrate ions bump into each other, they bump into each other and then whatever. Doesn't matter. There's no strong interaction. What about silver and sulfate?
Yes.
Yes. So really, what's the reaction that's happening? Is silver nitrate reacting, or is it specifically just one of these things that's reacting? Just one of. Do you understand where I'm going with this? Like, are both of these things reacting with something when we pour them together with a new solution? Is the nitrate doing anything? No. So could we have ignored the nitrate from the beginning? Yeah. Which one of these isn't doing anything? Sodium. Sodium's not doing anything. So the silver and the sulfate, they will deposit themselves at the bottom of the beaker. So you start to get a precipitate at the bottom. But did the sodium ions and the nitrate ions, did they change in any way or shape or form? No, they didn't. What we just did is we thought through, and we're making what we call a net ionic reaction. That's us caring about only the things that change. Again, I'm going to ask you this kind of one last time. Did the nitrate change? No. Did the sodium change? So we can ignore them. That's the idea behind this. Okay? So when we look at making a net ionic equation, a net ionic equation just says, show me the stuff that actually does something. Don't show me the stuff that just sits there and bounces off things the whole time. Okay? We want to ignore what we call the spectators. What does it mean to be a spectator? Have you ever heard that term before? Yeah? What does it mean, Akua? If you're the spectator of a football game or something like that, are you in there making a difference? Are you the one doing all the work? Well,
in a big stadium.
yes, in a big stadium you can make a difference, okay? Thank you very much, Idris. But no, you're not the ones actually putting in the work, are you? You're just sitting back and watching, so it's almost like you're not there. For a lot of competitors, it's almost like you're not there. So this is not the first time we've seen net ionic equations. It actually is, but that's fine. The goal of writing a net ionic equation is to focus solely on the ions that are actually involved in a chemical reaction. There's a series of steps. We're going to follow the series of steps, but at the end of the day, it's all about what in here is actually reacting. Step number 1, write a balanced equation for actually what's going on. Step number 2, dissociate all high solubility ionic compounds and ionize all strong acids to show that they're complete ionic equation. So Basically what step number 2 is saying, if it will split up, split them up. If it will split up, split them up. Because I want you to look at your table of acids and bases again. Does hydrobromic acid actually exist in water? Look for hydrobromic acid.
Yeah.
Does this actually exist? Is this chemical, does it exist when we put it into water? No, it doesn't. Okay, I know, just stick with me. When I put this thing into a beaker of water, 100% of it will turn into H3O plus and Br minus. 100%. There is no HBr in a solution of HBr. That sounds stupid, but we've talked about it before, correct? Have we talked about it before? Yes. In a solution of hydrobromic acid, there is no hydrobromic acid. I want to be very clear about that. What is there in a solution of hydrobromic acid? Hydronium and bromide. Why? Why is there only hydronium and bromide? Because this ionizes 100%. What do we call a substance that ionizes 100%?
It's a strong acid.
It's a strong acid. Because this is a strong acid, it completely splits up. Totally 100%. So, do we have HBr in a solution of HBr? No. We have hydrogen or hydronium ions, and we have bromide ions. So that's all it says. Step 2 is, if it will split up, split it up. Write that it splits up. Then what we're going to do is we're going to cancel identical entities that appear on both sides and write the net ionic reaction reducing coefficients if necessary. Let's. The only way to learn this is by actually doing it, so let's do it. Write the net ionic equation for the reaction of aqueous lead 2 nitrate with aqueous sodium iodide. I want to let you know that this is going to be very long, like wide, okay? It's going to be a little bit of work. So if you're lazy, if you're just lazy bones, okay, this is going to really suck for you. But if you don't mind putting in a little bit of work, a tiny, itty-bitty, infinitesimally small amount of work, this is going to be no problem. But if you're lazy, oh man, be prepared for a world of hurt. Write the net ionic equation for the reaction of aqueous lead 2 nitrate with aqueous sodium iodide. What two things do we have reacting together? Lead 2 nitrate. What is the formula for lead 2 nitrate? Pb NO3 Is this thing aqueous?
Yes.
But it tells you that it's aqueous, so yes. What are we reacting it with?
Sodium iodide.
Sodium iodide. What's the formula for sodium iodide? NaI. Aqueous. What do you think these two things will create? First of all, what type of reaction is this? It's double replacement. So both of the metals are going to swap, or both of the nonmetals are going to swap. It doesn't really matter as long as they change partners. So who's the lead going to be partnered up with?
Iodide.
So we're going to get lead 2 iodide, right? The lead 2 still exists. So what's the formula for lead 2 iodide? PbI2, right? And I don't know what the state of matter is, so I'm going to leave it blank for now. And what else? What else are we going to get? Sodium nitrate. And I don't know what the state of matter is. Okay, let me be fantastically clear. If you don't get the proper chemical formulas of all 4 of these things, you're hooped. Immediately you're done the question. It is not possible to get anything else correct if you do not get all of these chemical formulas correct, okay? So that's why we really wanted to stress making chemical formulas at the beginning of the semester. Please look and tell me, is this soluble and is that soluble?
First one solid, and the second one aqueous.
First one is solid and the second one is aqueous. Okay, is this a balanced chemical reaction? No, it's not. So balance it for me, please. Is that okay? 1, 2, 1, 2?
Yes.
Yep, good. So now, have we successfully, let's go back to the instructions, have we successfully written a balanced chemical reaction?
Yes.
Woo! That's what I'm talking about. Okay, what about number 2? What's the next thing? Everything that can be dissociated, dissociate it. In here, what's the only thing that cannot split up? The PBI2. So you got to split up everything. And this is what I mean when I say you need a lot of room. So do not write big for this step. Okay? You're going to need a lot of room, and you're going to see why we need a lot of room. Yes or no, the lead-2 nitrate can split up because it's aqueous.
Yes.
Yeah, it's ionic and it's aqueous, so let's split it up. How many leads are we going to get when they split up? We're going to have 1. 1 Pb2 plus aqueous. And how many nitrates are we going to get?
2.
We're going to get 2 NO3 minuses aqueous. Any questions about that so far? That this substance, when it splits up, makes 1 lead and 2 nitrates. Good?
Yes.
So all we're doing is the same thing here, right? We're saying that in my beaker of silver nitrate, we don't really have silver nitrate, we have silver and nitrate. Same thing here. In our beaker of lead nitrate, we don't actually have lead nitrate. We have lead ions and nitrate ions. Okay, what is it reacting with? It's not actually reacting with lead or with sodium iodide. It's reacting with what?
2 sodium ions.
2 sodium ions. And how many iodide ions? 2. Why 2? Why is it 2?
Because the 2 connects to both of them.
Because the 2 affects both of these things, right? 2 iodide ions. Remember, they need charges. They totally need charges. Okay. Can the lead to iodide split up?
No.
Then don't split it up. Rewrite it in the exact same way it's written there. Can the sodium nitrate split up?
Yeah.
Yes. How many sodiums will we get?
2.
2 sodium ions. And we will get,
2.
damn it, I was really hoping I'd have enough room. 2 nitrate ions. Shoot. Oh. Would you agree that took up a lot more room than some other reactions that we've written so far? Right? Because when we split these things up, naturally everything is going to spread out on our page. Okay, I want to ask you, when you look at this black chemical reaction, is there anything that doesn't look like it's doing anything? Is there anything on here that is common on both sides? Nothing about it has changed in any way, shape, or form. The sodiums, we started with 2 sodiums over here. And what did we end with? 2 sodiums. And did they change state of matter? No. Did they change charge? No. Just cross them off. You've got 2 NAs here and 2 NAs here. So it's almost like the sodiums didn't do anything. We're ignoring our spectators. What's the other spectator here? So the nitrate, the two nitrates and the two nitrates are gone. They're not gone, they're still there, it's just that they're not doing anything. Okay. Let's rewrite everything that we didn't cross off. This is our net ionic reaction. What net means is like overall reaction. I'm literally just copying down everything that I didn't cross off. That's the answer.
Do you have to write all that?
If I'm asking you for your work, yes.
Okay.
But if it's a multiple choice question and it just says what's the net ionic reaction for this reaction, then you just boom. Yeah. Yeah. Okay, so does it make sense? Just like over here, when we put the two beakers together, it was just the silver ions and the sodium ions. Once they bumped into each other, right? They bumped into each other and then they hugged each other and they didn't want to let go, so they made a precipitate. Same thing here. The lead 2+ ions and the iodide ions, when they combine, they just hug each other, they make a precipitate, and they never let go. That's the only change here. Any questions about that? No? Do you want to do another one together? Yes. Well, your only options are do another one together or do it by yourself.
I'll do it together.
Hands up for together. Hands up for by yourself. What? Oh, the togethers have it. We're going to do this quick, okay? We're going to do this real quick. Write the net ionic equation of the reaction of metallic copper with aqueous silver nitrate. What does metallic copper look like?
It's a solid.
Cu solid. That's metallic copper, right? If it's a metal, if it's metallic, that means it's elemental and it has no charge. It's an atom. Okay, with aqueous silver nitrate. What does silver nitrate look like? Ag. Ag what? NO3. It's a 1+ and a 1-. So what are we going to get from this? It's a single replacement. So what's the copper going to kick out? The Ag. The Ag is going to get kicked out, kicked to the curb. We're going to get copper nitrate. But how many coppers and how many nitrates are going to be in my final compound? So first of all, what's the charge on the copper going to be? How many nitrates do we need? 2 of them. We need 1 copper and 2 nitrates. And if you check the solubility table, it's going to be aqueous, because nitrates are always aqueous. Okay, but what do we get? We get silver, and it's going to be an element, right? So solid with no charge.
Why is it an element?
Pardon?
Why is it an element?
Because when you kick out, this is an element plus a compound gives an element plus a compound. So, okay. Have we made a balanced chemical reaction? Absolutely not. Okay. So we need 2 of these and 2 of these in order to balance it. Now, have we made a balanced chemical reaction? Yes. What's the next step?
To split everything up that isn't solid.
If it can be split up, let's split it up. So on the next line, can copper, elemental copper, split up into something? No. Okay, all right. Copper solid. Can silver nitrate split up? Yeah. How many silvers are we going to get? How many nitrates are we going to get? can the copper nitrate split up? So how many coppers are we going to get? How many nitrates are we going to get? And can the silver split up? Just the silver all by itself? No. I made the gravest of grave mistakes. I should be taken out back and I should be beat with a copper pipe. Okay? Because this is such a horrific thing to do in a chemistry class. What did I do, Roy? What didn't I do? Yeah, I didn't put in the charges. So should the copper have a charge over here? Yes. Yes. Should the copper have a charge over here? Yes. No. It's elemental. Should the copper have a charge? No. Thank you. No. Okay, the copper over here should not have a charge. Why? It's an element, and elements are atoms. They don't have charges. Should the silver here, should it have a charge? Should the silver here have a charge? Where did it come from? An ionic compound. So I got to write down the ionic charge, right? The nitrate should have a charge. Here, should the copper have a charge? Yes. Good. Do you understand why I'm asking these questions?
Yeah, so it doesn't mess with the combined.
Yes. Good. Okay. Is there anything in here that doesn't do anything? Is there any spectator that we want to kick out? No. Okay, let's go one at a time. One at a time. Okay, look at the front. Copper. Does copper change in any way, shape, or form?
Yes.
Yes, it does change. Does it change? Yes, super duper, huge change. This is a massive change. This is the biggest change in the world. This is going from an atom to an ion. That's a huge change. Can we cross off copper? No, it definitely changed. What about silver? Can we cross off silver? No.
No, it changed.
Did it change?
Yeah.
Yeah, big time. This is silver ions floating around the solution, and it turned into a chunk of silver metal that you could use to pay for things. That's a huge change. Okay, I cannot cancel out the silver. Can I cancel out the nitrate?
Yes.
Yeah, the nitrate didn't do anything. NO3 aqueous, NO3 minus aqueous. Yeah, that. Okay. So, what's my net reaction? What is our net reaction? You literally just rewrite everything you didn't cross off.
Does this develop? Thank you.
What?
Does using net equations like develop, or is this just burden?
Oh, we can do lots of stuff from there. Yeah, this is the purpose. The purpose of writing a net ionic equation is to boil everything down to just show. I just want to show you the stuff that actually changes. I don't want to show you all the crap that doesn't do anything. Okay? We've got two laws for equations, don't we? What are our two laws for equations? Law of conservation of mass and conservation of charge. Does this follow, this net ionic reaction, does it follow the law of conservation of mass? Yeah. One copper, two silvers, two silvers. Good. Does it also follow the law of conservation of charge?
No.
Yes.
No.
positive on the left-hand side and 2 positive on the right-hand side, right? I have a total of 2 positive, and I have a total of 2 positive. Because I have 2, here, the 2 positive is just all on 1 ion, right? But here, there's 2 positive ions floating around. So yes, it does. Are we okay with this?
Yes.
All right. Okay. I'm gonna help you start this one, and then I'm gonna let you kind of skedaddle on through here. I hate this part of the course because you just learned about something, and then now I'm gonna force you to kind of erase part of your memory temporarily, just right now. Is that okay? Okay? Yeah. We have to. Okay. Hydrochloric acid. Does hydrochloric acid exist in water? Look at your table. Where's hydrochloric acid in your table of acids and bases? Is it a strong acid or a weak acid? It's a strong acid. So does hydrochloric acid actually exist in water? No. Why don't strong acids exist in water? Because I'm going to write this down, but I don't want you to write it down, okay? When I put HCl in water, what I want to know is what percentage of this will be left over?
All of it.
Like, well, all of it turns into this, right?
1%.
So yeah, less than 1%. And by less than 1%, we mean 0.00000000000000001%. It's not quite 0%, but it's not quite 1%. It's less than 1%. Okay? So that means all of this, or greater than 99% of it, is going to ionize. Right? So when I put hydrochloric acid in water, is it really hydrochloric acid?
No.
It's hydrogen ions and chloride ions. Now, to be more specific, again, do hydrogen ions exist in water? What's more appropriate? Do you remember? Hydronium. Okay, but we're going to simplify it, and we're just going to think about it as hydrogen ions. Is that okay? We're not going to write it as hydronium. We're just going to simplify it and write it as hydrogen ions. So let's start the equation, and then I want you to do a few of these, and then I'll bring you back in about 10 minutes. So write the net ionic equation of the reaction of hydrochloric acid. Hydrochloric acid. What's the formula for hydrochloric acid? HCl aqueous. Perfect. And aqueous, barium hydroxide. What is barium hydroxide? It's Ba and OH, right? Anything wrong with that? Yeah. 2 what? 2 bariums or 2 hydroxides? 2 hydroxides. Ooh, man. OH2. That is, why did I write the state of matter as aqueous? Because it literally told you in the question. Just roll with it. Okay. What are we gonna get? What's gonna kick out what?
Hydrogen. Water.
The hydrogen, which can act as a positive ion, right? Hydrogen can act as a positive ion, is going to kick out the positive ion. See, what are you going to get when I combine hydrogen with hydroxide? What are you going to get? HOH or water, right? H2O. I'm going to write HOH. I'm going to write HOH because it's easier to balance it that way. And barium, what's barium now left with? The chloride, right? So BaCl2. Now I know that water is a liquid. Hopefully you know that water is a liquid too, at room temperature, okay? But barium chloride, is barium chloride Is that soluble? It is?
Yes.
Okay, good. Is this a balanced chemical reaction? Sure doesn't look like it. Okay? What's the most complicated thing in this list?
The last one.
I would say the second one.
Yeah.
Okay? 1 barium, 2 OHs. So you need, think of it this way, the OH at the end here is the same OH here. So how many OHs do you need? 2. So how many hydrogens at the start do you need? 2. And then that'll balance out. So go ahead. Can hydrochloric acid split up?
Yeah.
It's a strong acid, so split it up. Can barium hydroxide split up? Look at the state of matter.
Wait, if it was a weak acid? would it-
If it was a weak acid, most of it does not split up.
So you wouldn't.
So you would not split it up. Okay? Barium hydroxide, can it split up? Look at the state of matter. Yes. If you check your data booklet, it will tell you no. But I need you, and this is where the nuance of looking at the question is so important. It says aqueous barium hydroxide, so it's telling you that this barium hydroxide has split up, okay, because it's aqueous. So can you do the rest of this? If you finish it, go on to the next one, please. I'm going to be wandering around, and I'm going to be helping people. Yes.
Wait, can the liquid split up?
Are you going to ask them or no?
If it's water, can the liquid
Water is a molecular compound. Molecular compounds split up. What are the only 2 types of compounds that can split up? Strong acids and high solubility ionic compounds. No. Plus, 2 chlorates, yes. apologize, I'm writing so small because I want to fit it all on the board, but Tommy, do you have any questions? Okay, do you want me to read it out for you? The last one? So it's Ba2 plus aqueous plus 2Cl minus aqueous. 2Cl minus aqueous. Yep. So is there anything I can cancel out, or does everything cancel out here? No. What's going to cancel out? The Cl and the Cl. What's else going to cancel out? The barium and the barium. And what am I left with? So I'm left with our net reaction, 2H plus 2 hydroxides gives us 2. You could say HOH or H2O, it doesn't really matter. It's all the same thing. Now, I want you to look at this net reaction, and something might pop out to you as being weird here. Something might kind of like catch your eye, and you're like, "Oh, that's interesting." Idris?
Is it the 2 H's?
It's not the 2 H's. The 2 H's came from the 2 HCl's.
No, like how many H's are?
Oh, does this follow the law of conservation of mass? Yes, it does. Does it follow the law of conservation of charge? Yes, it does. 2 pluses and 2 minuses make neutral, and there's neutral over here. What do you notice about all of the coefficients? So, all of the coefficients are 2.
Oh, that's not
Okay? And typically that's not allowed, right?
Really?
Yeah, like when you're balancing a reaction, you always have to take the lowest coefficients, the lowest group of coefficients. So instead of having 2, 2, 2, what could I have? 1, 1, 1 would be fine. If you divide all of them by 2, it would be 1, 1, 1. Now, if you didn't do that, I'm not going to take off marks, okay? But I just want you to realize that I could have said 1, 1, 1, and that would probably more completely reflect what's actually happening. There's 3 extra problems here, and I would like you to try them out. And I'm going to put up the key in about, 15 minutes or something like that. So you go ahead and try these out. Let me know if you have any questions. Yep. Yep.
But it's not busy, right?
What do you mean? Like it doesn't get busy?
It's busy, but it's not busy all the time, right? At the end, it's crazy. Work with yourself.
Fire away.
So when the copper goes off, does it become an ion, or does it stay just an ion?
Okay, what you have to understand
Which one?
is it an ion to begin?
Yes.
Yes. And a single replacement reaction is always element plus compound
Yeah.
gives compound plus element. So this is going to become an element.
Okay.
Do elements have charge?
No.
Does that answer your question?
Yes.
Yes. Cool. Just double check.
Is that wrong?
The first one?
Yeah.
Yes.
Is it just because of the copper I have to?
Correct. It should not have a charge. Why? Why should it not have a charge?
Element?
Because it's an element plus a compound plus a compound. Also, look at your reaction. Does it follow our two laws?
No.
No, it doesn't follow our law of conservation of charge. So that charge is wrong. It should be 0.
Mhm. So if we went from here to here, it's gonna be stay the same, just copper.
Nope. Nope.
Like copper without.
Like go ahead and erase that. Oh, from here to here, yeah, it's the same. Yeah. All you're doing from this step to this step is you're just splitting things up if they can be split.
Yes.
Right? So zinc can be split up. Copper 2 sulfate can. Zinc sulfate can.
Here we put the charge because we take the zinc from the.
Because the zinc is in an ion compound. It's an ion, right? Yeah. So this charge needs to disappear.
Yes. And here I will put
Two lines. Awesome.
It's so cute though. Where's my actual detail booklet? Oh, this is trash to the point. I don't use it. Because Hubble is not what you do. No problem. This is what I do. Just in case. Okay, so you see how much of this one is the first week? Okay, it's gone through the garbage can and came back out. Goodbye. Wait, is zinc an element I'm serious. So elements don't have charge. Yes. Yes, they don't have charge.
If I toss a chunk of metal, like, yeah, if I toss a chunk of like Does that make sense? Okay, the only difference between here and here is they can be split. So the zinc can't be split up. Good. The copper 2 sulfate gets split up into copper 2 sulfate in this state. The zinc sulfate gets split up into zinc and sulfate in this sulfate. Okay, and then what happens? That's totally different. Why, what happened, that last thing, the last thing in both of your equations, they're totally different. Like radically, totally radically different. What's the difference between this and this? There's like a huge margin. Oh man, that is not the same, not even close to the same. I get that it's still a C and U, but they're totally different, right? Yeah, do you want me to show you what copper looks like? Yep. One of these was the top one, and one of these is the bottom. Are they the same thing? I'm not even. Oh, that right? Which one is this?
Oh, yeah.
I'm not trying to buzz you more. I'm just trying to. Yeah, that's copper, right? Copper 2 plus is this, right? World of difference. So it very much matters if you have the chart. Okay. Okay, so now, so it can't change at all, right? All you need is spin. Okay, so what is not the same between here and here? The zinc. Okay, so write an arrow, draw an arrow. Okay, on the left-hand side, the zinc was solid, right? Okay, so on the left-hand side, so is there more than one zinc on the left-hand side of the arrow? You know what I mean, Dan? Yeah, but you're not done yet. Yeah, the copper, they're not the same. You cannot cross their ancestors. There you go.
And how did the color change from?
What do you mean how?
Like how
It
did
reacted or something.
like it's came in liquid.
Yeah, but this is dissolved in water. Okay, let me be a little bit more honest.
I made it for you. You look so good. Thank you. Weird.
So one of these is copper metal in water, and one of these is copper ion. Which one is copper metal? That one. This one is copper metal. Now you're asking me how did it go from this to this? And what did it react with? Or react? You know what I mean?
Yeah, it's here. It's copper sulfate.
Yes.
Yeah, under it.
And so if I take something zinc, okay, watch what happens. Now the blue isn't going to disappear, okay, but we're going to see a chemical reaction. When I dip this thing in here, okay, I'm going to dip it in Is it different?
Yes.
Yeah, the copper plated, it turned into copper metal on here. It's just that it looks black right now.
Yes.
It's such a blue-green color that it's black. Alright, so the zinc turned into zinc ions, and the copper ions turned into copper metal.
Oh, okay.
Yeah.
Thank you.
Okay. I'm going to give you like a couple minutes to finish up whatever questions you're working on. Yes, there's many questions. Great. So what is that? So okay. So does that mean that he was distracting you? He was distracting me. Yeah, I don't know what that.
I did this one.
This one? Oh man. Oh, classic rookie mistake, Kylan. Yeah. One of your states matter is wrong, my friend. Go back to your original, go back to your original equation. Okay. Does it say it's a solution? Okay, but whatever, that's fine. It's silver nitrate solution, barium acetate. Okay, they're both solid. So whatever, that's fine. Okay, let's go to these two. One of these states of matter is radically increased. You better believe it is. Yeah, that specific example is so drastic. Do you see what's going on? Yeah. Okay.
What happened? You do actually, and then yes.
Yeah, I just have a mild concern.
I hate you.
Oh, I just put that. I just put that.
Okay, perfect. Okay, that's awesome. Okay, that's awesome. Do some
This is a dissociation.
You don't want.
I thought it was, oh yeah.
Yeah, this one.
So what do you think?
That's association. There's one here.
Okay, that's what it's two silvers.
I don't, there's not even association.
Ready?
Oh. Association all aqueous stuff. Oh yeah.
Yeah. Well, you gotta balance it. Okay, but also we're missing something. Let's go back to your original equation. Did you find it? An ion. Right? Yeah. Oh, baby. That's what I'm talking about. So now we can just cross it. Yeah. Okay, there's 3 minutes left. Ooh, and my watch is dead, so that's fine. I want you to listen up, please. And, I don't want to do that. So write the net ionic equation of the reaction of metallic zinc with aqueous copper 2 sulfate. I'm not going to show you all the steps, but I am going to show you the answer. Are we ready for the answer? Yes. 3, 2, 1. Oh. Yeah, I was writing on an angle. That's okay. So zinc plus copper 2 sulfate, but the copper 2 sulfate split up. Made zinc sulfate, which splits up. Right, so the sulfate in the sulfate doesn't do anything. So it's zinc plus copper 2 ions makes zinc 2 plus ions and copper metal. I want to be very, 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 very clear about this. Okay? This is what a solution of copper 2 ions look like. Is it can you spot this from a mile away? Yeah, a blue liquid kind of looks like Kool-Aid, don't drink it. Okay? What does copper metal look like in water? It looks like a chunk of copper sitting in water. Do you understand? Can you appreciate why I'm stressing so badly the difference between copper metal and copper ions? Right? This is a huge difference. There's extra practice if you want, but otherwise, I'll see you on Monday. Have a good weekend. No, but it's not going to hurt to do it.
Where's the extra practice?
There's extra practice at the very end.
You can't take it, honey. It's already there.